Hello again, everyone. This section is on measurement of work. So we start with work done by a constant force. So work, which we'll usually represent with a W, is force times distance. So sort of a basic example. Let's say we have an elevator and it's lifting a 200-pound passenger. A total of 210 feet. So pounds are actually a measurement of force. So then the work done by the elevator, force 200 in pounds, times our distance 210 in feet. So the work done by that elevator, we would just multiply those two, and then the result will be in foot-pounds. 42,000 foot-pounds of work. So that's if it's a constant force. So 200-pound person, they're standing still, they're not bouncing up and down. Variable force, that's where the calculus comes in. So some simplifying assumptions that we make. Yes, in Calc 2 we still make some simplifying assumptions. We're going to assume the object moves on a linear path. And we're continuously applying force. We'll call that force f of x. And we'll do that from x is a to, you shouldn't be super surprised here, x equals b. In this case, then, the work is the integral from a to b of cap f of x times dx. So this is going to be kind of the basis for most of our work in 7.5. So one application of work would be Hooke's law. Hooke's law has to do with springs. Force is equal to k times distance in Hooke's law. So the force applied to the spring is equal to some constant having to do with the nature of the spring itself, what material it's made of, how many coils per inch or per foot or whatever we're measuring, that kind of thing. Difference between an annoying clicking pen spring and a spring on the front fork of a motorcycle. K would be very different for those two. So K is just a constant of variation. So just a quick problem in Hooke's law. So force of 40 pounds compresses a spring that is 2 inches from its natural length of 12 inches. So we're going to find the work done to compress this spring into an additional 4 inches. Now, as you can kind of guess, the more you're compressing the spring, the harder you have to push to get the next little bit of distance out of the next little bit of compression out of it. So we'll start with our force of 40 pounds. We don't know K at the moment, and the distance that the 40 pounds was able to compress the spring was 2 in inches. So here K is going to work as long as the force is in pounds and the distance is in inches. So then K, as you can see, is 20. And we're going to let distance equal x. So then cap f of x, 20 times x. So the force is 20 times whatever distance. So then the amount of work, integral from when we started compressing again, it was at 2 inches past its resting point. We were compressing it an additional 4 inches, so 6 inches of compression total, so 2 to 6 of our force, 20x times dx. So now our work, 10x squared, evaluated from 2 to 6. So now our work is 320, and this will be in inch pounds this time, as opposed to the elevator problem that was in foot pounds. So 320 inch pounds of force to compress it the additional 4 inches. All right, so another common application of work involves emptying tanks. So this next one is going to be a excuse me, a right circular cylinder. So here is our lovely 3D rendering of a tank, and a little bit of information about this tank. So the tank is going to be 10 feet tall. And we're going to have 6 feet of water in the tank. And the tank itself has a radius of 3 feet. So if we draw sort of an arbitrary little rectangle here, an arbitrary disk on it, this will be our delta y. Here would be our y. So then the remainder would be 10 minus y left. So y plus 10 minus y gives us the total of the 10 feet in height. All right, so some other information that we have. So we have the 10-foot right circular cylinder filled up with 6 feet of water. Pump at the top is going to empty it. So here, we'll put a little dot there. There is my fantastic rendering of a pump. So we have a pump at the top. Its job is to empty the tank. And one other bit of given information. The water will weigh 62.43 pounds per cubic foot. So we're going to find the work to empty the tank. So change in force is the change in the weight. So our weight, they gave us the weight of water based on a number of cubic feet. So first let's find out how many cubic feet of water that we're going to use. Well, right circular cylinder, the volume, area of the base, pi r squared, times the height. We're going to have delta y as our height, change in height, times the 62.43, the weight per cubic feet. So this is pounds per cubic feet. This one was a number of cubic feet. So notice the cubic feet are going to drop. Okay, so delta F, then a little plug and jug on the calculator, 561.87 pi delta Y. So that is our change in force. So change in work is change in force times a distance. So change in work, change in F, we just found that. 561 and 87/100 pi times delta Y. Our distance, the distance that we are traveling to go from the arbitrary sort of 2D rectangle or 3D disc that we made, it's going to go from Y units in height up to the top, so it's going to travel 10 minus y in distance. So change in work, a little distributive property there, so 5,618 and 7/10 pi minus 561 and 87/100 pi each times delta y. So we just went ahead and distributed. So then W would be the integral of that. And where we're working, the water is as low as 0 feet and as high as 6 feet. And we're still multiplying by dy. So we find our antiderivatives. And I lost my y along the way. My apologies. That's why it looked a little weird to me. Okay, antiderivative of a constant is the first power. So 5,618 and 7/10 pi times y. Antiderivative of y is y squared over 2. And we're evaluating this from 0 to 6. So the work done, 23,598 and 54/100 pi foot-pounds. If you want to get a decimal approximation, throwing in the pi there, let's see, that ended up at 74,136 and 9,999 10,000 foot-pounds. So one thing the author does is occasionally has us check to make sure that the answer is reasonable. In this case, I would argue that it is reasonable if we look at the total weight of the water. Flip here. We had 54 pi cubic feet of water. (62.43 pounds per cubic foot). So 3,371.22 pi. And that is in pounds. If we do just work as force times distance, well, our minimum distance is 4 feet, but some of the water is going all the way up 10 feet. If we just take the low end of 4 feet, our force times our distance, here's our foot-pounds. So notice that is quite a bit under it, but again, this is estimating just based on moving at the minimum of 4 feet. Only the water at the very top of the surface moved only 4 feet. The water at the very bottom of the barrel moved an entire 10 feet. So it is a reasonable answer. We are reasonably close here.